Let's jump right into this explainer and tackle a notoriously tricky challenge from the 2002 British Mathematical Olympiad. Now, the goal here wasn't just to blindly guess an answer, but to construct a complete, bulletproof, logical proof. We're hunting for all the positive integer solutions for three variables, a, b, and c. And this isn't just your everyday algebra. It involves factorials. You know, those numbers that multiply all the way down to 1 and just explode in size incredibly fast. At first glance, it feels like we're staring at an infinite ocean of possibilities. But as we're going to see, logic is an incredibly powerful tool for reigning in infinity.
So here is our main culprit. A factorial times b factorial equals a factorial plus b factorial plus c factorial. Right off the bat, there's a really cool trick we can use. Because multiplication and addition are commutative, meaning it completely doesn't matter what order you do them in, we can safely assume a is simply less than or equal to b. Think about it. If a equals 2 and b equals 3 works, then 3 and 2 is going to work just as well, right? So without losing any generality at all, we just pin a as the smaller or equal number. It's a tiny assumption, but it's the very first magnifying glass we're going to use in this investigation.
All right, here's our roadmap for cracking this case. Step 1, setting boundaries. Step 2, the contradiction squeeze. Step 3, forcing the variables. And finally, Step 4, finding the unique solution. Let's start cornering these suspects. Step 1, setting boundaries. Here's where we prove that a absolutely must be at least 3. Let's just interrogate these smallest possible numbers first and see what happens. We know our variables have to be positive integers, so let's check out 0, 1, and 2. If a is 0 or 1, a factorial is 1. Plug that into our equation, simplify, and you end up with 0 equals 1 plus c factorial. Well, since a factorial is literally always positive, that's impossible. Okay, what if a is 2? We plug that in, the algebraic dust settles, and we get b factorial equals 2 plus c factorial. But hold on, think about the factorial sequence for a second. 1, 2, 6, 24, 120. They grow explosively. There are absolutely 0 factorials in existence that are exactly 2 apart. So just like that, suspect A is cornered. It has to be 3 or greater. Moving on to step 2, the contradiction squeeze, where we prove B is strictly less than C. Now that we've got a bound, we're going to use a bound. We're going to use a classic mathematical detective technique, proof by contradiction. We basically assume the exact opposite of what we want to prove just to watch the math completely break down. We want to prove B is less than C, so let's play devil's advocate. Let's pretend B is actually greater than or equal to C. If B is the biggest number, then a factorial, b factorial, and c factorial are all smaller than or equal to b factorial. Add them up, and the absolute maximum value of the right side of our equation is 3 times b factorial. But wait, look at the left side, the product. We already proved a is at least 3, meaning a factorial is at least 6. So the left side must be at least 6 times b factorial. You see the problem? 6 times something cannot be less than or equal to 3 times that same thing. Our lower bound is way heavier than our upper bound. The scales are broken, which means our assumption was completely false. B definitely has to be less than C. Real quick, before we jump to the next phase, a tiny refresher on divisibility notation. When you see a vertical bar between two numbers, like m bar n, it just means m cleanly divides n. No messy decimals, no fractions, just a perfect fit. Keep that in your back pocket, because we're about to use it to blow this case wide open. All right, step 3, forcing the variables. Time to prove a must exactly equal b. Let's build an inescapable logical trap. Again, we'll assume the opposite, that a is strictly less than b, and see what breaks. We divide our whole original equation by a factorial. This transforms it into b factorial on the left, and 1 plus b factorial over a factorial plus c factorial over a factorial on the right. Now follow me here. B is at least 4, so b factorial is definitely an even number. The right side has a 1, which is odd. That third term, c factorial over a factorial, because c is larger than b and b is larger than a, dividing them leaves a product of consecutive numbers, which means it's inherently even. So for an odd number plus an unknown plus an even number to equal an even total, that middle unknown term, b factorial over a factorial, absolutely has to be odd. But how is that possible? Factorials multiply consecutive numbers. If b is 2 or more steps larger than a, dividing them leaves an even number. The only way it stays odd is if b is exactly 1 step larger than a. So b equals a plus 1. But when you plug that back into our formula to test it, the algebra completely collapses and forces a to equal 0. And we already proved a is at least 3. Contradiction complete?
A and B have literally no room left to hide. They must be exactly equal to each other. Finally, step 4, the unique solution. Let's prove C is less than or equal to A plus 2 and nail down the final answer. Okay, since A equals B, we substitute that in, and our giant equation shrinks down to just A factorial minus 2 equals C factorial divided by A factorial. We just need to corner C. And divisibility by 3 is going to do the heavy lifting here. We know A is at least 3, which guarantees A factorial is a multiple of 3. Now, if you take a multiple of 3 and subtract 2, the result is for sure not divisible by 3. That means the right side, C factorial over A factorial, can't be divisible by 3 either. This right here is the nail in the coffin for infinity. If C was 3 or more steps larger than A, dividing their factorials would leave behind a product of 3 consecutive numbers, and any 3 consecutive whole numbers will always contain a multiple of 3. Always. So to keep multiples of 3 out of our equation, C can't be 3 steps away. It can only be 1 step away, or 2 steps away. That's it. C must be A plus 1 or A plus 2. Let's test the first option. What if C equals A plus 2? Substitute that in, crunch the algebra, and it simplifies down to A factorial minus A squared minus 3A equals 4. Notice how every single term on the left is a multiple of A? That means A itself must cleanly divide 4. Since A is at least 3, the only divisor of 4 that works is 4 itself. But, as any good detective knows, a confession isn't enough. The evidence has to match. When we plug A equals 4, B equals 4, and C equals 6 back into our very first original equation, it fails. The left side is 566, the right side is 768. Dead end. Which leaves us with literally only one mathematical possibility in the entire universe. C equals A plus 1. Substitute it in, and the algebra elegantly collapses to A factorial minus A equals 3. Using that exact same logic, A must divide 3. And since A is greater than or equal to 3, A absolutely must equal 3. We finally have our suspects. If A is 3 and B equals A, then B is 3. And if C is A plus 1, then C is 4. Let's plug 3, 3, and 4 into the original equation and see if the magic happens. Left side, 3 factorial is 6. 6 times 6 is 36. Right side, 3 factorial is 6, plus 3 factorial, which is 6, plus 4 factorial, which is 24. 6 plus 6 plus 24 is exactly 36. Nailed it! Out of an infinite ocean of numbers, only 3, 3, and 4 fit the lock. As Mind Your Decisions, the source for this explainer, points out, this is just a wonderful problem. The beauty here isn't just getting the numbers 3, 3, and 4, it's the elegant logic required to squeeze infinity down to a single undeniable answer. We didn't use a supercomputer to brute force millions of combinations, we just used pure human reasoning. We built walls of logic, boundaries, contradictions, simple divisibility rules, until the numbers literally had nowhere else to go. So next time you're facing down a massive, seemingly impossible problem, think about our suspects, A, D, and C. Ask yourself, where can I start applying the squeeze? What's the absolute minimum boundary? What happens if I assume the exact opposite of what I want? Often, a problem that looks infinitely complex can totally be unraveled if you just know which logical threads to pull. Until the next explainer, keep squeezing those problems and stay curious.